Okay, last section of chapter 5, 5.9, the simplex with upper bounds and lower bounds. So we've hinted at this. Again, it's not something you have to implement in your MATLAB code, but you could. And it's also good to know the algorithm exists, and it helps understand why, like for instance, MATLAB and other production code has you give an LB and an UB vector. Okay, so let's look at this example. It's given to us here on the left, and then we put it in standard form over here on the right. Two variables, Z1, Z2, two main constraints. Then we have these two bounding constraints, which really can be thought of as these four separate constraints, right? Z1 is greater than 0, but Z1 is also less than 6. Z2 is greater than 0, but it's also less than 5. So when we split this, we have 4. And then we're going to use that to create our set of inequalities here. So these two here become equalities this way. So we're actually adding Z3, Z4, Z5, Z6. So there's 6 total variables with 4 equality constraints. So that's how we would have handled it, standard form, to run simplex by hand or run your MATLAB code by hand, or your own generated MATLAB code. But had we looked at it over here, we would have just entered it into MATLAB with 2 vectors, a lower bound vector and an upper bound vector, UB. Now, why were we doing that? Because MATLAB can actually handle, it has its own code, simplex, that works with lower bound and upper bound. So the standard form for lower bound, upper bound LP is we're minimizing or maximizing some linear function C transpose X. We turn it into equality constraints, but it's okay to have not X greater than or equal to 0. You could have some L vector and some U vector, right? And again, this is the standard form. MATLAB actually doesn't even have you make equalities, right? They can handle a less than in their linprog and int linprog. Okay, just note that the U, any element of U could be 0 or it could be infinity or any number in between. It could be 6 in here and 5 as it is. And the lower bound can also range from minus infinity to 0 or 2 or minus 10 or whatever, right? So just letting you know that you can enter those as infs. All right, so then if we take this as the standard form, this is what our model would look like to put this problem in standard form LBUB, right? So there's 2 types of standard forms that we have now, our classic standard form, and then this new, more sophisticated way, UB-LB standard form, and it would look like this. So we still make our inequalities into equalities, but we're allowed to leave Z's as ranging between a left value and a right value. And then our table display would look like this. We starts very similar, C, A, B, and now we're just going to add these 2 rows at the bottom. L, that's the vector. Again, in MATLAB, we're not adding our slacks, so we're just adding the 0, 0, and the 6, 5. But doing this by hand, doing simplex with the table method, we do have to add where the lower bounds on these are artificial slack variables and the upper bound, and they go from 0 to infinity. Okay, let's make some more space. Okay, I just want to give you an idea of how this algorithm works. Again, you don't have to code it. We're not going to work them by hand either, but it's going to help you when you're setting up your models to put into the production code. So let's think about the basic simplex method. A basic solution set non-basics to 0, and it solves AX equal B for the remaining basics. Because again, it pulled out some columns in that, right? It's really was solving a BXB equal B. So what do you think we're going to do for the lower bound, upper bound case? Rather than setting those to 0, because that really was the lower bound there, we're actually going to set it to either the lower bound or the upper bound. We'll talk about that in the algorithm. And then you're just going to solve for the basics, right? You're going to do the same thing. Now let's think about in this simple simplex algorithm. A basic solution was a basic feasible solution of BFF. If all the basics were greater than or equal to 0, we only had to satisfy those non-negativity constraints. What do you think is going to happen for the lower bound, upper bound case? Well, a basic solution becomes a basic feasible solution if it satisfies the bounding constraints. So it has to be between L and U for every basic variable. And that actually creates an algorithm. So we're going to look on page 278 is algorithm 5D. That's our lower bound, upper bound simplex. And I forgot to mention on page 271, the revised simplex. So again, if you want to go for some bonus points and challenge, win the MATLAB coding competition, you could implement that, and that is on page 5C. That'll guide you. I'm sorry, algorithm 5C on page 271. Here's a couple of our homework problems. Don't forget to copy those down. But before we conclude, let's go to our books and look at these algorithms. So 5D. Okay, so here's our lower bounded, upper bounded simplex. Choosing a starting feasible solution. Again, same problem that we've always had. Might need to do a two-phase or a big M. Okay, and then you're computing reduced cost, and notice these are slightly different. We're not just doing a C transpose X. We have a little bit more going on here. Your optimality rule, if none of your reduced costs indicate improvement, then you're optimal. Otherwise, you're going to choose an entering and a leaving variable. And you're going to set we have this new thing, this new little indicator delta, which is saying if you were at an upper bound, you need to go away from that to maintain feasibility. So you need to set your delta to -1 if you're upper bounded. If that non-basic variable was at its lower bound, then it has to go away from that, which would be in the positive direction. So delta would be +1. So that's what that part is for. Then we're going to choose a simplex direction. That's, again, the greatest work for us, except the thing that changes here. We're still doing the revised simplex was B delta XB times -A I. Well, here we have to add this delta, right? The delta is telling us whether we're going above the lower bound or below the upper bound. Step size. There is a rule, another rule of the minimum ratio test changes slightly. So go back to 5.52. Check out that rule quickly. Box 5.52. So again, we're going to have because we can go above or below, we actually also need to split our step size lambda into a lambda plus and lambda minus, but very similar, right? Our very similar min ratio test. Instead of just xj, we now need to say how far can we go towards that lower bound or the upper bound, right? So that's why the numerator changes slightly. And then delta is there, that's that an indicator variable of whether we're going towards our way. So hopefully all these make sense. There's slight tweaks to our standard algorithm. And then our usual update rule. Okay, but again, major work here in the simplex direction, and we've already talked about ways of reducing that, which was back on page then 271, algorithm 5C. Here we go, this box 5C. So here is that revised simplex where we're being smarter in the most expensive step, the simplex direction. We are just solving the smaller system, B delta X equal -AI. And we're using that repeatedly. And then if we want to do, it's not in this book, but if we want to be even smarter, we do it with Sherman, Morrison, Woodbury, and do the rank 1 update idea. Okay, that's the end of chapter 5, simplex, the greatest algorithm, one of the top 5 algorithms of the last century.